So, were this a quiz today, there would be some sad people in the room. And if that's you, and let me be honest, it's many of you, I don't want to hear the phrase, when's the makeup? Okay, I walked around the room a lot just now, and I was actually asked very few questions. That's a big warning to me. If you don't have progress here, and you're asking me when the makeup is, well, what if this was the quiz today? What would you say? You weren't prepared? Let's see. Let's see how much, information is just what we've been doing for the last 6 weeks. We started with the free body diagram, and you guys all, I can't say agreed, but you at least identified that these are the likely forces acting in the system. Good so far? I notice at least one of them appears to be unbalanced. Would you agree? Can we all also coalesce around this is the one that appears unbalanced? I'm saying that because I walked around to a lot of tables and I didn't see the simplest of things like net force in the x direction equals ma. That's the unbalanced one. That's the x direction. That's pretty simple. And that also suggests then that net force in the y direction must equal 0. Pretty simple. Right? You can't really blame me on this one. I'm going to have to blame you guys. Now I'm going to ask another question. This one's tough. Is the object traveling in a circle or is its speed changing? Meaning, is it getting faster or slower, or is it traveling in a curved path? I'm not trying to fool you. I'm just asking this guy. Is the acceleration he's experiencing making him go faster or slower, or is it making him change direction? I asked it 3 different ways. Circular motion, curved path, or change direction. They all would have to be MAC. Again, not trying to add a lot here. But once I put AC there, I have 2 options. I have V squared over R, or I have omega squared times R. Ultimately, it doesn't matter which of these I choose, but one of them is easier than the other. Am I being asked about the object's linear velocity or angular velocity? I'm being asked about its angular velocity. The problem specifically said, find the speed must the ride spin in RPM. That's angular velocity all day long. So I'm going to use this one. That means net force in the x direction equals m omega squared r. In fact, this is what I'm solving for. How fast does the ride spin? A lot of you miss that. Like, you don't know what to solve for. That's what I'm solving for. That's my unknown. Now I'm going to continue to go through the simple steps for Newton law problems. Add up all the forces in the x direction and set them equal to this. There's 1 force in the x direction. I walked around. I know who was able to do this and who wasn't. I fear when I see people not writing this kind of stuff down when they need to, and what we did to get here. I'm using the exact same set of procedures I've been using the whole year when it comes to net force problems. Add up all the forces in the y direction and set them equal to 0. There appears to be 2. I have F pointing up and mg pointing down. All right, that's it. That's all that Newton's laws can do. I've used them all the way to the end. They produce 2 relationships that may or may not be able to help me solve my problem. Right now, I'm going to say may not. I don't know what the normal force is. I can probably find the frictional force because I have M and I have G. There must be something that helps me with this, something that can help bring these things together. And I've said this a couple times. Maybe you should write this down, that whenever you're dealing with friction, it is the frictional force that brings the normal force into the problem, right? There's a relationship between normal force and frictional forces. This is an additional piece of information that's required for any problem where the coefficient of friction is being used. How do we know to use this in this problem? I'll give you a really big hint. I say the words, coefficient of friction. Pick one of them. You got two. Two different equations. One with an inequality, one without. This one's static. It takes the inequality. So what do I do now? I gave you a hint. Whenever there's an inequality, substitute into the inequality. I have normal force. I have frictional force. I'm going to substitute into the inequality. So mg must be less than or equal to mu m omega squared r. Again, I'm not doing a whole lot of thinking, a lot of substituting. And I do want to point out something very important. I gave you the mass because I knew some of you couldn't do the problem without it, because you sub your numbers in really early. And you would have said, how am I supposed to find out the frictional force if I don't have the mass? You would have said those words. I would have heard you say them. And I'll reply to you. You don't need the mass. Have you ever been asked how heavy you are before you've gotten on a ride? It would be a bad design. So the mass is actually unnecessary. On a test, I wouldn't give you the mass just to make you have to prove that to yourself. Even now, some of you don't know what to do next. Well, we're solving for omega. I can solve for omega here. Just did algebra, divided both sides by mu times r. I'll probably take the square root. Not terrible. Nothing new for sure. Boy, I'm tired of these Newton's law problems. You might be too, but until we can, not have only a quarter of the class get this problem, we might have to practice more. Even now, I have a few of you who probably still can't get 22 and a half. This will not give you 22 and a half. This is 10 divided by 0.6 times 3. And then take the square root. It's like 2.4 or 2.36. That's because it's 2.36 radians per second. I asked for RPM. That makes it 22 and a half RPM. I don't know if you can go from here to here, but I see you guys writing feverishly. Great. It's a greater than or equal to, which means I have to spin the ride at least this fast. The minimum is 22 and a half, but I probably should spin a little faster in case somebody's clothes are a little slipperier. Right? You do see that the 0.6 is in the denominator. If that number gets bigger, then I can spin the ride slower. Right? It's in the denominator. Do you guys see that? I'm saying to you, if I asked you what would happen if you made mu bigger, could you say to me you could spin the ride slower? Because I would expect that you know that something in the denominator made bigger makes this whole side smaller. I'm expecting that. Look, I could also make the radius of the ride bigger. That would let me spin the ride slower too. But maybe I want to spin it faster, so maybe I'll make the radius smaller. That's why they closed the one at Busch Gardens. The radius was too small. People were getting sick. They're turning around too many times, too fast. Oof. We chose to use the expression that had omega in it because we wanted a rotational speed. So if I look here at the units in this portion of the problem, it's the square root of, the top is in meters per second squared, that's G. Mu has no units, right? It's a unitless quantity, but R is in meters, okay? So I have meters and meters, those would cancel out, leaving me with the square root of 1 over seconds squared, right? Because the meters canceled out, so the numerator has no units. So this is just 1 over seconds. But this is a rotational speed. So radians are a unitless quantity on their own. We talked about that a little bit, but I'm still not sure you guys fully appreciate it. When you know you're dealing with something rotational and you work it out and it comes out to be unitless, then the units are radians. So that's what makes this radians per second, okay? The default is radians, not rotations, all right?